Good evening, my name is Benjamin Cieslinski. I am a master's student at the University of Houston Clear Lake, and my research project is entitled Particulate Exposure Assessment of Metal Casting Operations in a University Foundry. So let's start with an introduction. What is the foundry? Universities teach metal casting and foundry operations as part of a standard mechanical and construction engineering curriculum. From small-scale casting operations, students gain practical experience in handling molten metals, producing custom objects, and further their metallurgical studies. Numerous studies on the health and physical hazards of industrial foundry operations and their workers have been undertaken since the early 1900s. But since small foundry operations are on a drastically reduced scale from industrial applications, they receive very little attention. And also, since university foundries are under the auspices of general laboratory safety programs, routine exposure assessments of small foundry operations are rarely performed. So, foundry processes are divided into ferrous and non-ferrous metal castings. Ferrous and steel foundries are large-scale productions that produce products that weigh thousands of tons using very high temperatures. While large-scale ferrous operations of iron and steel manufacturing make up over 80% of the total American foundry output by weight, non-ferrous foundries such as aluminum, brass, and bronze are much more common and produce small parts and fittings with much smaller outputs. In industrial settings, different parts of the foundry process are performed in separate areas with specific health and safety precautions and must follow strict regulations on worker health and safety. NIOSH has had guidelines in place for foundry operations since the 1970s, and all foundry workers are covered under OSHA rules. But at universities, instead of ferrous foundries, we generally use the lower melting point of aluminum, about 666 degrees Celsius, and the low cost of scrap material as a major factor in choosing aluminum for teaching casting. The lower melting point allows for small electrical or gas furnaces and standard steel tools to be used rather than specialized temperature-resistant materials and coke-fed furnaces. Many hobbyists and artists also use the small scale, even homemade foundries, due to their simplicity and low cost. In the small scale and limited physical space of university teaching laboratories, these operations are commonly contained within a confined area, such as a purpose-built laboratory. The coalescing of practices into a common area increases the possible exposure to toxicants and hazards associated with these processes unless engineering controls are included into the design. Now, universities commonly teach what's called the lost mold method of casting. The typical teaching foundry processes include the four following steps: the preparation of the molds, the melting and casting of metals into molds, the cooling and removal of the molds, and the finishing of raw castings. The lost mold method involves the creation of a mold with a top and bottom form that contains the cavity in which the molten metal is poured. The form is created by pressing dense sand around an initial object, then removing the object, creating a negative space for the molten metal. The sand must be able to be compacted and allowed to bind, therefore maintaining its structure when separated from the original mold. Green sand is also commonly used, and it is a mixture of sand, clay, and carbonaceous earth, which normally has a chemical binder, including some generic organic solvents, and it's very common. In industrial settings, the melting of metals is performed in large batch couple furnaces that use coke and air to heat the metal to its melting point. The furnaces require the control of input gases and oxygen intrusions and are very expensive to operate. Small-scale foundries found in teaching programs melt aluminum metal in what's called a crucible furnace. Now, this type of furnace contains a refractory crucible inside of a ceramic shell heated with either electricity or fired with natural gas. The equipment is relatively small and easily controlled with minimal oversight, yet the high temperatures reached during melting also produce a litany of particulate emissions, including metal particulates and fumes. And the pictures you have here shows the industrial cupola, and also the one on the small scale is actually a homemade version for a hobbyist. Now, pouring the molten metal into the sand mold is a manual process in small-scale foundries. The crucible is raised from the furnace using temperature-resistant tongs, normally requiring two people to properly lift and pour the metal to minimize spillage. Once the molten metal hits the sand casting, any chemical compounds included in the sand for bindings are volatilized due to the high temperatures. This process also involves inorganic fumes from minerals trapped in the sand particulates. After the casting is cooled, the sand mold is broken off of the casting and discarded. The finishing process begins by the removal of the gadding by mechanical saws or grinding. The casting is then cleaned using grit or tumbling devices to smooth out any burrs or imperfections in the casting. To create a smooth finish and remove any chemical oxides that may have formed during casting, sandblasting and grinding are commonly used. These physical processes fracture and break down the metal and sand particulates into smaller sizes that are then spread throughout the foundry atmosphere. So let's discuss the history of particulate hazards in the foundries. Respiratory disorders were common among early foundry and metal workers. Industrial hygiene studies from the 1920s found pulmonary fibrosis in nearly a quarter of steel casting workers. Workers involved in the sandblasting and finishing of metal castings were found to only have a 1 to 2 year window of good health before they would be normally stricken with debilitating lung diseases. Foundry workers were also discovered to have a mortality rate from lung cancer that was 133% higher than the expected rate. During the 1950s, many studies were conducted in the U.S. that positively correlated respiratory diseases, including bronchitis and lung cancer, with a chronic exposure to one particulate, airborne silica. Silica, also called silicon dioxide, also called quartz, is one of the most common ingredients on Earth. It's found in rock, sand, and soil, everywhere. The chemical properties of silicon dioxide molecule allow it to form intermolecular bonds with itself to form crystalline silica superstructures. These superstructures can form either in amorphous clusters, such as glass, or in repeating patterns of crystalline silica. Naturally occurring silica crystals are too large to be considered a health risk since their particle size is normally too large to reach the alveoli of the lungs. Instead, these particles are trapped either in the mucosal lining of the nose or throat. The foundry processes, though, physically alters the structure of silica crystals. Crystalline silica structures are formed when the sand used in creating molds is exposed to rapid heat during casting. Also, the grinding, sandblasting, tumbling, and shaking of the molds physically breaks down the sand particles into much finer subdivisions called respirable quartz. Respirable quartz includes the common crystalline forms of silica that makes up quartz, cristobalite, and tridymite. These fragments are kept aloft in the atmosphere longer due to the decrease in their settling rate, which increases the chance of them being inhaled. These fragments are small enough that they can penetrate through the turbulent airflow and branches of the nose, throat, and lungs and reach the gas exchange membrane of the alveolar spaces. Upon reaching the alveoli, the body's defense mechanism of pulmonary macrophages attacks any foreign particles and releases enzymes to break them down. Unfortunately, the macrophage enzymes cannot destroy silica, and instead damage the alveolar surfaces, creating scar tissue. The scar tissue disrupts the gas interchange and results in both decreased oxygen flow into the blood and a decrease in carbon dioxide exchange from the blood. This is the cause of the occupational lung disease called silicosis. Symptoms include shortness of breath, cough, bluish skin, chest pains, infection, and fatigue. Long-term studies have linked silicosis to an increase of respiratory failure and lung cancer. Lung cancer mortality data in foundry workers, especially those exposed to abrasive silica particulates, showed an increase of death three times higher than workers without the exposure. Small-scale, specific construction tasks were also monitored, including concrete cutting, the use of hammer drills, and masonry. Results from these studies by sampling airborne particulates resulted in recommendations of various engineering controls and personal protective equipment to reduce silica exposure. Besides silica exposure, metal fumes are a serious threat to pulmonary health. During the melting of metals, some of the metal can vaporize and later condense into fine airborne particulates called fumes. These fume particles are very small, normally less than 100 micrometers, and stay aloft for very long periods of time. When metal fumes are inhaled, they can reach the alveolar spaces. Metal fumes have the same effect on the macrophages as silica and can create the same scarring tissue. If exchanged in the lungs, these metals can be a source of toxicants that are linked with pulmonary and cardiovascular damage, neurological and kidney disorders, and cancerous neoplasms. Aluminum fumes have been directly associated with tingling in the extremities, nausea, asthma-like symptoms, neurotoxic disorders, and early onset Alzheimer's. Occupational exposure of metal fumes has been studied to determine exposure levels in welding operations. Those studies resulted in the recommendation of standard engineering controls, including elephant trunks, venting fumes away from welding operations. Other small-scale operations included jewelry repair and dental filling engineering. Any health hazard that may arise from airborne particulates must be correlated with exposure rates. In an industrial foundry worker, the long-term chronic exposure data is collected and compared with health and safety standards. Since all aspects of foundry operations occur in a confined space, to determine if our students or staff in a university foundry are at risk of acute or chronic exposure of silica and metal fumes, an exposure assessment must be performed. The legal limit of exposure is determined by OSHA's permissible exposure limit for respirable silica and aluminum dust. This limit does not represent the desired exposure level below which harm cannot occur. Instead, NIOSH's 8-hour recommended exposure limit and ACGIH's threshold limit value are used as benchmarks for safe practices. The purpose of the project was to assess the human exposure to respirable silica and aluminum fumes during routine university foundry operations. The assessment was performed by collecting air samples from the area during foundry operations and measuring particulate concentrations by an AIHA-accredited laboratory. The significance of this project is to minimize the acute exposure to hazardous particulates created during small-scale foundry operations. Startup foundries, schools, home casting projects, and hobbyists will benefit from knowing what kind of hazard exposures can occur during the casting process. The sampling data for this project was collected at Texas A&M University at Qatar's Hot Works Laboratory, Room 22. The room is used for university foundry operations, for teaching welding processes, and for equipment storage. The 32 by 25 foot room layout is shown in this slide. Space limitations for storage and safety concerns force the foundry operations to be performed in an area around 10 by 10 square feet located in the center of the room. There is an exhaust air vent connected to a central air system located about 20 feet above the center of the room, but there is no return air vent into the room. 2 wall-mounted air conditioning units do not pump fresh air into the room. Instead, they use cooled liquid to circulate and cool the room air. These designs were implemented to reduce the amount of airborne dust entering the room, which is a major problem in the desert environment of Qatar. The sampling of the air for respirable silica was performed by following the modified method NIOSH 7500. NIOSH 7500 method was developed to determine the percentage of major silica polymorphs in respirable silica, the quartz, cristobalite, and tridymite, using X-ray powder diffraction, or XRD. During the XRD analysis, X-rays are passed through a sample and are deflected as they pass through a crystal. From this information, the crystal structure and composition can be determined. The sampling of the air for aluminum fumes was determined using NIOSH 7300. This method was developed to determine the concentration of metallic elements in air filter samples by inductively coupled argon plasma atomic emission spectroscopy, ICP-AES. An ICP-AES uses inductively coupled plasma to excite the atoms of the sample, which then radiate electromagnetic radiation specific to each element's molecular characteristics. This method provided simultaneous environmental analysis for a wide array of trace elements, including aluminum. The sampling requirements for NIOSH 7300 are very similar to the sampling requirements for respirable silica, with only some minor alterations in the sampling air rate and filter composition. For sampling, a pre-weighed polyvinyl chloride or mixed cellulose filter, depending on the method, was placed into a filter holder. For the silica sampling, a cyclone was attached to the filter cassette. The cyclone was required to remove any silica that was larger than the respirable limit of 10 microns. The filter assembly was attached to a pre-calibrated air pump to sample the air at the recommended rates of 2.0 and 2.5 liters per minute for the aluminum and silica respectively. This method required a sampling volume of around 1,000 liters of air. Every morning, the sampling pump's flow rates were verified and recorded. After calibration, the sampling apparatuses were attached to stands at a height of 5 feet on the perimeter of the foundry operations to sample the air in the breathing zone. 3 samples for each assay were collected during the foundry operations during an 8-hour period work shift. During the work shift, 2 complete castings were performed in their entirety by qualified staff. The castings across the sampling plan were of the same size and used the same amount of molten aluminum to reduce variations between castings. The 3 sampling stands were placed on the 3 sides of the pour site, including directly next to the crucible furnace, with each stand holding a sampling pump and filter for the aluminum and silica assays. Since all aspects of the casting and finishing processes occur in this relatively confined area, the sampling arrangement sampled the same breathing air as the personnel and allowed the daily samples to act as replicate samples without interfering with the casting process. A field blanket was collected for each assay during this period for analysis each day. The process was performed over 4 days, resulting in 12 observations with 4 blanks per aluminum and silica assay. After completion of the foundry task and the sampled air volume was reached, the filter samples were removed and sealed into a certified shipping container with chain of custody. The NIOSH methods required complex analysis using analytical instruments. Therefore, the samples were sent to Galston Laboratories for the analysis by an AHIA-accredited industrial hygiene laboratory. The preparation of the sampling molds took much more time than anticipated. To ready the molds, the green sand, which is actually red brick in color, must be passed through a series of sieves to break down the larger compacted pieces and remove any leftover metal slag. This process, along with the mold compaction, took up to an hour per mold and required a large amount of physical exertion. The green sand was easily spread and dispersed around the area and was tracked via foot traffic. The furnace was also set for a temperature of 1450 degrees Celsius, much higher than the 660 degrees required to melt the aluminum. This was done to have the aluminum pieces melt quicker, but also increase the possibility of multiple variants of crystalline silica forming. At the start of the pour of the molds, a large amount of whitish smoke was emitted from the mold. This smoke possibly included the metal fumes and silica particulates, along with carbon soot from the heating of the mineral oil included into the green sand. This odor was strong and stale. The outer door was opened right after the pour to reduce the amount of smoke inside the room due to the lack of ventilation. Participants complained that without the outer door being opened, the haze would never fully dissipate. Even with the outer door open, the smoke and odor lingered in the room for several hours after each pour. Before the sampling period was completed each day, the room was swept to contain the spread of the green sand back into a pile near the pour site, possibly spreading smaller particles back into the atmosphere. Every morning at the start of the sampling, you could see a very thin layer of reddish dust was visible on the floor and the surfaces of the sampling area. The finishing step of grinding and polishing was never actually performed. The castings are used mostly to teach casting techniques and to show metal stresses under high temperature, so no finished castings were ever actually produced. The castings, once cooled, were washed in water and were only given a quick polish with fine grit sandpaper by hand. The physical processes that would have broken down larger silica crystals were not seen. In these photos here, the one in the upper left-hand side was not taken during the sampling analysis, but it's using the same materials and processes that we used. The other three photos are the molds that were created, the castings, you can see the spread of the green sand all over the place, and the sieves and how much it actually does spread the green sand around. The expected results for this project will be shown in a data table comparing the 8-hour time-weighted averages of the sampled foundry air to the OSHA PEL, NIOSH REL, and ACGIH limits for respirable quartz and aluminum particulates. It is expected that the sampled concentrations may approach the NIOSH and ACGIH exposure limits, but will not approach the OSHA PELs. So the results came back, and let's talk about the respirable silica first. For the respirable silica assay, no sample was found to have collected any respirable silica in any of the three crystalline forms within the quantitation limits of the laboratory. That is, silica was seen in the sample, but the concentrations were below the calibration limit. This was unexpected as the high operation temperature of the furnace, the 1450 degrees Celsius versus the 660 required to melt the aluminum, was reasoned to be a factor in the creation of multiple crystalline silica forms. Also, the physical process of sieving the green sand and the violent compaction was thought to break down the silica into smaller particles that were flung airborne. The elimination of the grinding finishing process may have had a significant role in reducing the airborne particulates. For the aluminum samples, no sample had aluminum in any form at concentrations above the laboratory's level of quantitation. We had the same problem this time. Aluminum was seen, but it was below the low limit of the calibration curve. This result was also unexpected, especially due to the high operating temperature of the furnace again. It was reasoned that the excessive heat of the furnace would volatilize the aluminum to a much greater extent, but it simply was not seen. The haze and smoke emitted during the molten metal pours into the green sand castings was assumed to contain much greater quantities of the target analytes. Without performing a composition analysis of the smoke for a wide range of materials, the smoke composition can only be speculated. The green sand's binding compound was pre-mixed mineral oil, a mixture of heavy alkanes distilled from petroleum. When the high temperature molten metal hits the green sand, the mineral oil coating the sand undergoes incomplete combustion, forming carbon monoxide, carbon dioxide, and soot, raw carbon molecules. Depending on the amount of oxygen available, the smoke particles would perhaps be an amalgam of combusted alkanes and this raw carbon. The total respirable dust was collected and would have been used to determine the PELs of the silica forms if necessary. Instead, the respirable dust is the only measurable analyte that can be used to determine if the sampling area and location of the sampling trees have any effect on exposure. Site A samples, which were closest to the crucible, were all quantifiable, while both Site B and Site C had at least one day where the respirable dust concentrations were below the level of quantitation of the laboratory. In this case, we're going to make the assumption that the maximum possible concentration of the respirable dust concentration for those 2 days. When you put these figures into a graph, the graph demonstrates a relative consistency of the particulate concentrations during the sampling across the 4 days. The consistency of the concentration change across the sampling days is due to the maintaining of the same procedures, the same metal casting amounts during the sampling window. The location of sampling site A and sampling site B near the crucible showed no dramatic increase in the amount of respirable dust emitted from the molten metal that was predicted. This was likely due to the fact that the cover of the furnace was securely fastened during the melting and only opened briefly, less than 30 seconds or so, to extract the crucible. The increased respirable dust concentrations during the first sampling day was probably due to the time spent moving equipment and buckets of the green sand, positioning all of the goods to start the actual analysis during the initial casting process. Based on these comparisons, concentrations did not approach any of the standard exposure limits. No further engineering, administrative, or PPE controls need to be recommended for the control of respirable silica or aluminum particles. The low exposure rate for these particles does not eliminate the need for area assessments and exposure measuring for other possible airborne hazards from the casting process. The pour circulation in the room should be addressed to better remove the smoke and haze after the pour. Further analysis of the chemical content of the smoke from the casting should be performed to determine if the incomplete combustion of the mineral oil found in the green sand can be controlled. The amount of respirable dust collected may infer an overexposure to nuisance dust or smoke particulates generated from the casting process. And if castings are to be prepared that require a full finishing with mechanical grinding and polishing, the amount of particulates in the air will need to be assessed. I'd like to take a moment to thank the following people for their assistance: Ms. Marnie A. Smith, Director of the Office of HSSE and Building Operations of Texas A&M University at Qatar, for her financial support of this project and to your encouragement. I'd also like to thank Mr. Khalid Hasiba for his time, energy, and patience in teaching me the proper foundry techniques, and also Dr. Dennis Casserly of the University of Houston Clear Lake for his guidance and reviews. Below you'll see the references for this project, and the images used and the photographs. Thank you very much. Enjoy.